All right, here, let me start another solution. Here it says, when released, a 100-gram block slides down the path as shown, reaching the bottom with a speed of 4 meters per second. How much work is done? How much work does the force of friction do? All right, so my logic of attack, as I tried to explain in the video lectures, is to say the energy you start with will equal the energy you end with. This is a conservation of energy type of problem. And so you can write out all the different types of energy. For example, we have the initial kinetic energy, we have the initial potential energy, we have what we call the work done by a non-conservative force. That has to equal the kinetic energy final at the bottom. It also has to equal the potential energy final at the bottom. So that's, I guess, how this gets expanded a little bit. And even this can get expanded because when it comes to potential energy, we have the mgy, or sometimes just called mgh. But we also have the 1/2 kx squared for the two potential energies, one because of gravity and one because of the elasticity. Now, again, you can write all those out in detail, but I don't think there's any point to really even mentioning the 1/2 kx squared in the potential energies because there's no springs involved. Now, there is height involved, so the mgy on both sides is going to be important. There's speed involved, so this is going to be important. And then this non-conservative work, this is what we said would be the friction and maybe any other thing tied to it, like a tension, I said, a cable or something. And we don't have that. So this term here would be only the work done by the force of friction. So what this boils down to is we want to solve for that one. All right, so continuing on, I would say what's the initial kinetic energy? So up here at the top it says when released. So that kind of implies zero speed, and since kinetic energy is 1/2 mv squared, I'm going to put zero kinetic energy. Then here I'm going to put mgy initial. That's the potential energy. As we said, there's no elastic energy, so I won't need to worry about that. This is what I'm looking for, the work done by the non-conservative force. Then there would be a kinetic energy, 1/2 mv final squared. It is moving down here at the bottom. And then potential energy, the height here would be 0. And we're going to ignore elastic energy. So this just means that the work done by the non-conservative force would be 1/2 mv final squared minus mgy initial. So if I put these in, I have a 1/2. The mass is 1/10 of a kilogram. Watch your units. I say 100 grams, but remember, energy is measured in joules, and joules has buried inside of it things like kilograms, meters, and seconds. So I'm going to put it in kilograms. Again, the speed at the bottom is the 4 meters per second squared. So again, putting it in kilograms and meters per second, this is all a joule. And then I would have, again, the mass, and g is 9.8, and the initial height is 2 meters. And again, kilogram, meter, and then be meters squared over second squared. So all of this is in units of joules. Okay, so putting my numbers in here, I've got a 1/2 times a 0.1 times a 4 squared minus 0.1 times 9.8 times 2. And this is a negative 1.16 joules of energy. And I'm real happy to see a negative sign because when we worked out the work and we had this integral of the force of friction and then some distance involved, Oh, and cosine of the angle. The angle between the friction and the direction it moves is 180 degrees. If it moves, say, to the right, as it is moving along, the friction is to the left. And so they're 180 degrees apart. Cosine of 180 degrees was a negative, and then the force of friction was a constant, and then we just got the distance traveled. So, I think I put it as a delta x. I think your book puts it a d, and I did a delta x. So, the work done by friction should be something like this. Now, fortunately, they don't ask us to do these individually, because that'd be really hard, because we have a hill that has a weird shape to it, so the distance traveled is pretty complex there. Moreover, the friction is related to the normal force, which is related to the slope, and so as the different slopes come into play, we have a different amount of friction. So we don't know what the friction is at any given instant because we don't really know the slope and all that good stuff. But we can answer this question, and so I think we just did. All right. Hope that one helps.